Hi! What I'm going to tell you about today is that I actually think we're in real trouble. That is, I think we actually have the foggiest idea how to compute very well. And I think that there are some small, glimmer of hope on the horizon in a number of different directions, which I may point out. Okay? But I think most of the things we've been talking about, even here, are obsolete. Okay? What I said to somebody after the Haskell session I went to, there was a workshop yesterday, is, gee, this is the most advanced of the obsolete languages. Okay? And what I mean is this, okay? See that? You now see the triangle that isn't there. Right? Everybody see the triangle that isn't there? Good. Okay? What did you do? It took only 100 milliseconds, or maybe 200 milliseconds. Okay? That means between your eyes and whatever it is that knew it was 100 milliseconds, certainly if you had to put on brakes if you saw something like that, right, and it was crossing the street. Okay, you know that's only a few hundred milliseconds, that's only a few tens of neuron times. I don't care how parallel the machine is. I have the foggiest idea how to write a program that organizes a complex process like that in a latency of about 30 or 40 steps. Now that's an example of something we don't understand how to do. Okay? And it's more serious than that. Okay? A human genome is about 1 gigabyte. That's the instructions for making you from a cell. Okay? It's a pretty complicated machine. 1 gigabyte is about the same size as the source code appropriate for, say, making Microsoft Windows. Right? It's not much bigger or smaller. It's something like that. Okay? So, we have all the possible things that it could possibly do and all the drivers that might be relevant and everything. It's probably that size. It's not much bigger. Let's put it that way. It's not 3 orders of magnitude bigger. And a gigabyte is not that big. But what's interesting is that with a small change to it, you make a cow instead of a person. So it's flexible too. Okay? So we've got this enormously flexible language there that we haven't the foggiest idea what it's like. I'm not talking about DNA. DNA is, that's something like Gates or something. Okay? What I'm interested in is the high-level language that's necessary to do things like that, and we certainly don't know how to do that. Okay? So now, what can we say about that? Well, I'll tell you one little thing, but maybe there's some hints. Okay? These biologists do nasty experiments on animals. And suppose you took a salamander. A salamander can regrow its limbs if you cut them off. So all these nasty biologists do things like they'll cut a limb of a salamander, a hand, the arm off over here at just between the shoulder and the elbow, and at the same time cut the same one between the elbow and the hand, flip around that segment, and resew it back on. Nasty thing to do to the salamander. But what do you think you get? Does anybody know? Does anybody here know? No, what you get is 3 elbows. It grows 2 new elbows to make up for the fact that the wrong thing is connected to the wrong thing. Okay? It's pretty weird. Okay? But there's a clue. That's a clue to something that we should be thinking about. About how do you talk about how to make a bazillion. That's what we're talking. A human's like 10 to the 12 cells. Okay, a salamander is probably 10 to the 11th or 10 to the 10th. I don't know. Okay, but the fact is that how do you make something big like that grow itself? The little neighbors talk to each other, and they say, "Oh boy, I'm supposed to connect to a thing like this, but it ain't there, so we'll make some of that." Okay, and that's the sort of amazing kind of process that's going to be necessary if we want to approach the future in our computing. Because by golly, it's almost impossible to set up a situation where we understand everything that's going to happen in the future. Let me go back and past a bit. Okay? When I started computing in 1961, this was a computer. This wasn't this particular one, but it was an IBM 650 at Columbia University that I was computing at. Okay? That machine cost $500,000. It had 2,000 words of 10 decimal digits each of memory on a drum that rotated so that the access time is 12.5 milliseconds. Okay? So think they get 10 milliseconds cycle time. Okay? And that the total amount of memory is probably about 10 kilobytes. Now, for the price of that machine, I can now buy 50,000 PCs, okay, literally, okay, each with a gigabyte of RAM. That's, that's 10 to the fourth times as much, and with, which is about 1 million times faster. Okay? So one of the things that's been happening over the years, I'm not trying to worry about Mr. Moore's law or anything like that. What I'm worried about is that all of our sort of intuitions from being programmers have come from a time of assuming a kind of scarcity, a world in which computation is expensive, where memory is somehow expensive, where we have to optimize it. Okay? Well, there are some applications like that. But the answer is most things are not like that at all. Right now, memory is free. Computing is free. It's our problem now to figure out how to use computing like that. And, if I had 50,000 PCs hooked up with an appropriate network, which would probably cost $1 million at that point, modern dollars, okay? Well, because you buy them in bulk. By golly, you can make a pretty serious computer out of that. Now, by the way, this machine took 30 kilowatts, if you're interested. I have the power plug from the 7094, which was somewhat more advanced, but that's a different problem. Okay, so it is no longer necessary to minimize operations. It is no longer necessary to worry about how much memory we take up. It is very important to minimize latency. Right? That's critical. We have to understand that. But the real cost of computation is not that at all. It's the cost of programmers. Okay? Here's a quote from Mr. Evans from Glasgow, made a while ago. It turns out that almost all the cost of computing is you and me. Okay? That's a different world. That's the real problem. Okay, so what are we going to do? Well, there's lots of things people worry about. Over the years, we hear lots of pundits worrying about things. People worry about correctness. Gee, that's a problem. Is it the real problem? Maybe. Probably not. Most things don't have to work. Look at Google. If it makes a mistake, it doesn't matter. Okay, so long as the next time it gets the right answer. Right? Or maybe something nice or close to the right answer. Something called reasonable. It needs a reasonable answer. Okay? What other kinds of things are there? Well, people worry about security. Well, they've got no idea how to handle security. We'll find out, for example, that humans managed to make it for about 70 years. We'd be continuously attacked by parasites. Gee, there must be some clever things we're doing. Okay? It's all in that gigabyte of code. Okay? We've got to think about that. We certainly haven't got any good ideas about how to make things that last for a very long time when continuously attacked by mutating parasites. Okay? Okay. Right? Okay, the other thing that seems really important to me is that we spend all our time modifying existing code. Okay? The problem is our code is not adequately evolvable. Okay? It's not adequately modifiable to fit the future. In fact, what we want is to make systems that have the property that they are good for things that the designer didn't even think of or intend. That's a big problem. Okay? That's the real problem I want to go after today a little bit. Okay? So what is this problem? The problem is that when we build systems, whatever they are, we program ourselves into holes. I've done it a number of times. I've been programming, as I said, since 1961. I found more ways to screw up than anybody I know. Okay? And I've learned a lot of hope, but not an infinite amount. Okay? And so here's this problem. Okay? Well, how do we keep ourselves from programming ourselves into holes? What does that mean? It means that we make decisions early in some process that spread all over our system, the consequences of those decisions, such that the things that we want to change later are very difficult to change because we have to change a very large amount of stuff. That's the problem. Okay? And I want to figure out ways that we can organize systems so that the consequences of the decisions we make are not expensive to change. We can't avoid making decisions, okay? But we can try to figure out ways to minimize the cost of changing decisions we've made. Okay, so let me start with a simple example, one that is so familiar that we all do it these days, certainly in good dynamically typed languages like Lisp or Python or whatever, or in good statically typed languages like Haskell or whatever. Okay, we always have something like generic operators. They call it operator overloading and things like that. Okay, let's talk about that for a second because I'm going to be very extreme about this. Okay, here's the traditional arithmetic you would find in scheme. Okay, I can add integers together, great. I can add integers to rationals. I can make new rationals. I can add integers to, quote, reals. Okay, they're, of course, floating point thingies that are very dangerous. Okay, and nothing brings fear to my heart more than a floating point number. I mean, numerical analysis, the blackest art I know. And, they just start worrying about this. It's terrible. But then again, we can deal with things like complex numbers and exact complex numbers, which are integer parts, and things like that. And that's okay. Okay? But, those things are built in. Okay? How about dynamically extensible generic operations? Now, we can do that. Of course, if you separate compile time and interpretive time or runtime, something weird is happening here. I mean, I want to be able to dynamically extend things while my program is running. I want a program to compute up what it's going to do. Okay? Remember in the old days when you used to program in assembly language or something, at least I used to do that. Yeah, it was a great language because you could write the next instruction you were going to execute. Okay? You could put it into the place where you were going to go to. It just was. And many interesting programs were written that way, and it was very flexible. There's too many fearful people, I can see a lot of people cringing, but the fact is that, you can do that in Lisp also. Okay? You can eval something you cons up. Okay? Boy, is that useful. But in any case, okay, so here I can do things like expand this to have arithmetic on functions. Now here's an example. I can add together sine and square right over there. Okay? And I've got a new function because that's a classical thing people can do in algebra or in mathematics. You say if you've got two functions with the same kind of input, then the sum of those is in fact assumed to be the sum of the outputs. Okay? It's a generic extension. Okay? That is for things that are of type procedure, if you want, of the right same number of arguments. I could talk about the sum of the square. Of sine and cosine applied to 2.5, and I get 1. That's right. That's what I should expect. Okay, good. Okay, that's an example of a simple extension. They can be simple, and by golly, you have all these nice things. I was watching somebody talking about Scala Z today, and of course you can do things like that. Okay, but then you get to things where Lisp does things better. There's symbolic algebra. Okay, now this is again a generic extension. I'm going to explain how it works, except that I can tell addition and subtraction, multiplication, division, all those things to deal with symbolic entities as well, literal numbers. Okay, and what I get is a symbolic expression as a result of such a computation. Okay, and I can, of course, the nice thing is that's a fragment of a program that came out. So I can write a program that writes a program, and then I can use it. I'll tell you a good example of a use of that. Okay, it's a numerical analysis example. Doing a gear integrator. Does everybody know what a gear integrator is? Anybody know what a gear integrator is? It's for something called stiff equations, differential equations. Okay? Turns out there's some polynomials that you have to compute up, and if you compute them up ahead of time, you only can do halving or doubling the step size. But if you want to be able to make the step size any size you want to be able to compute up the appropriate polynomial at the moment. So you write a thing that symbolically does that, then you pass that through the compiler as you need it, and then you run it and use it in the same program that's sitting along, integrating along. Turns out it's a great thing to do and great fun. Okay? But the point is that you can get essentially machine quality code. You're getting fully native code efficiency, except at the moment when you're changing step size to a funny step size. Okay? So that's a useful thing. That's why I like Lisp, because it has uniform representation of programs as data so that symbolic manipulations produce stuff that I can execute. Okay? Now, but you can do something even more wild. Did you know that automatic differentiation, does everybody know what differentiation functions is? And automatic differentiation can be done as a generic extension. What you do is you create hyperreal numbers. Numbers that look like x plus delta x, the same way the complex number is real part plus j times the imaginary part, or I if you're a mathematician, j if you're an electrical engineer. That's because of a French inventor used I for intensity, which is current. But in any case, you could do this sort of thing, okay? And you could say the derivative of the cosine, the sum of the cosine and the square function applied to x is, now I'm using, of course, my symbolic parts as well, so these things all mix together. Okay? This is the sum of 2x and minus sine x. So 2x minus sine x. Okay? And I can look at something more complicated, a derivative of a function of two variables, which is in fact a structure of the two partial derivatives, which is what it should be, because if I multiply that by an increment in the arguments, I should get an increment in the answer. And that's a matrix multiplication. This is, you look at a row vector coming out. Okay? That's the sort of thing that you can do very easily. Of course, I'll tell you the trick of how to do this, okay, just for fun. Okay? For those of you who are interested in things like this kind of trick, this is the kind of thing you're interested in. So if you take every possible, that was pulled out of Abraham Lincoln, actually, used that comment. If you extend things x plus dx and you have all your primitive functions, including things like addition, subtraction, multiplication, division, okay, and things like that, arctan with two arguments and things like that, produce an output which is f of x plus d of fx times dx, where dx is the thing that corresponds to the imaginary unit in imaginary numbers. Okay, then what you can do is you can just push things through that and extract out the df, which is the derivative of the function. Okay, now that gets you the chain rule instantly and automatically. Right? That's it. So you do a generic extension of all your primitive operations, and you get the automatic chain rule, which is right, and that's hard to do symbolically without any other way. But this works also numerically, at full speed, whatever you want. Okay, it's producing a composition in the same way you have combinators. Okay? So that's a useful kind of thing. Okay, and I actually use this all the time because I teach a class. In fact, I'm teaching one this term in advanced classical mechanics. It starts with Lagrange's equations and goes through canonical perturbation theory, and I use computer programming in my class and for these graduate students in physics and things like that. Use computer programming in this class to actually clarify the things we write on, when we write down these equations, because mathematical notation is both awful and it turns out ambiguous, and to be perfectly honest, it's impressionistic, right? It's very simple. Look, when I'm talking to you in English, it's the same phenomenon. Mathematicians talk to each other because they're almost all alike. Just the reason why you can understand me is we're almost all identical. Okay, and so only a few bits have to be transferred in order to get an idea across. If a mathematician's painting an idea in the Platonic world of another mathematician's mind, okay, by talking to them, and they write down basically impressionistic scribbles the same way my speech is not grammatical, beautiful English. Okay, but in fact, when we write programs, we have to be precise because computers are dumb at this point. And as a consequence, that's a great way to show someone the real story. Okay, and so I can write things like this, which is the definition of the method of computing Lagrange equations, right here, from a Lagrangian, given a configuration space path. Now, for those of you who don't know this sort of thing, it doesn't matter. I'm not going to dwell on it, but what this basically is you make a state path out of a configuration space path, which is a tuple of three things: the time, the path value at that time, and the derivative of the path value, the velocities. Okay, and you have to take the derivative with respect to the time, which is the capital D here, because that's derivative of one argument, of the result of getting the partial derivative with respect to the velocity argument of the Lagrangian, and you compose that with the state path, etc. Okay, and you get the right things here. And by golly, if you take a harmonic oscillator or whatever you like, you stuff in Lagrange's equations, and out comes the actual residual, which is equal to 0, which is Lagrange's equations. Okay, nice. Okay, now if you want, that doesn't matter for. What did I say? Okay. But that's easy stuff. What if I had to do something with the? No, I mean it. What if I'm dealing with something with a couple of rigid bodies that are wobbly and have all sorts of? Then I can't write the equations down on this board. Okay. In fact, if you do celestial mechanics like I've done, sometimes the equations are 20 pages long. Okay. And by golly, it better be done by a computer. The old days, people did it by hand. They got it right most of the time. It was amazing. It's amazing. I can't do what people did in 1911 or whatever. But it's quite amazing that they could do that sort of thing. And now we can do this easily. And it turns out that this is very simple because of the simple generic extension. Okay? Now, I'm not trying to claim that solves any important problem. Okay? Very careful about that. Okay? That this is a little tiny feeling of what is it needed to make things more flexible. Consider the value here. The value is that I'm dynamically allowed to change the meaning of all my operators to add new things that they can do. Dynamically. Not at compile time, at runtime. Okay? Programs can produce things which are the new way to add. Okay? That sort of stuff. And they can attach that to addition, and they can take it off and all that, and it can look like binding. I can bind that idea. Okay? That's wonderful. Okay? What does it do? What is it doing? It's giving me tremendous flexibility. Okay? Flexibility because the program I wrote to run on a bunch of numbers with only a little bit of tweaking suddenly runs on matrices so long as I didn't make the mistake of commuting something wrong. Right? If I did, I'm in trouble. Right? So this makes proving the theorems about things very hard. In fact, maybe impossible. And that's so the cost is and the benefit are very extreme. Okay? I can pay correctness, okay, or proofs of correctness or belief in correctness. I can pay that for tremendous flexibility right there. Now, again, we worry about ideas like, is correctness the essential thing I want? Look, I'm not opposed to proofs. I love proofs. I'm an old mathematician. Okay? The problem is that proofs, putting us into the situation that Mr. Dijkstra got us into about 30 years ago, 40 years ago, where you're supposed to prove everything to be right before you write the program. Okay? Getting yourself into that situation puts us into a world where we have to make our specifications for the parts as tight as possible. Because it's hard to prove general things, except occasionally, sometimes easier, but usually it's harder to prove a general theorem about something. So you make a very specialized thing that works for a particular case. You build this very big tower of stuff, okay, and boy, is that brittle. Change the problem a little and it all falls over. We didn't learn something from the electrical engineering I did, the digital abstraction, whereby the inputs to something accept much bigger range than the outputs are allowed to produce. And therefore, you get rid of noise at every stage. That's a kind of flexibility that I'm expecting to get, and I hope to get. Now, none of the old stuff, by the way, when you do this kind of generic thing, extensions, it doesn't mean that the old stuff breaks. It means the new stuff is not proved. Got to be careful about that. Okay, so many of the techniques I'm advocating make proof much more difficult and perhaps impossible. Now, I'm going to now be a little more extreme. I haven't been extreme yet. This is the beginning of stuff. Okay. I think one of the problems is the kind of architecture we're assuming. Okay? Everything in the world at least looks like my 650. Okay? It's very occasionally people have made wonderful things. A GPU is different, right? But or maybe, I suppose, the connection machine was an experiment which was different. Okay? But in the future, it's going to be the case that computers are so cheap and so easy to make that you can make them the size of a grain of sand, complete with a megabyte of RAM. You're going to buy them by the bushel, I suppose. You can pour them into your concrete. Okay, you can buy your concrete by a megaflop, and then you have a wall that's smart. Okay, so long as you can just get the power to them and they can do something, that's going to happen. Okay, it's sort of the way I said. Remember, your cells are pretty smart. They have about a gigabyte of RAM. a few bytes of RAM probably, or maybe a few hundred. We don't know how many, but they seem to talk to each other and do useful things. So we have to begin to worry about that kind of a world. Okay, well, I'm going to tell you a story that started around 1975, okay, and has recently had some advances. It's called propagators. It started when I was teaching my first classes in electrical engineering at MIT, in circuit theory, actually. Actually, the first class I taught was the field theory, but then I taught a circuit theory class with a real wizard of circuit theory, Paul Penfield. And I observed that what we taught the students wasn't at all what the students actually were expected to learn. That is, what an expert person did when presented with a circuit that looked like that was quite different from what we tell them to write down the node equations, and there are certain equations for the resistor and the capacitors and the inductors, which are none of them here, and the transistor, which has a complicated nonlinear equation, and then you're supposed to grind these equations together somehow and solve them to find out what's going on. But that's not what a really good engineer does. What a good engineer does, he looks at this thing and says, well, let's consider the bias analysis here. That means these capacitors are open circuits, okay? And that means that, therefore, and I'm going to consider this transistor to be beta infinite and be a follower right now, meaning its base emitter voltage is going to be 0.7. That's an assumption based on the assumption of how we're using it. It might actually be wrong, in which case I might have to back out of this. Okay? Given that there's no current into the base here, there's no current going into this capacitor, so this is a voltage divider. Since I know the voltage here and I know the voltage here, I know the voltage here. Therefore, I know the voltage here, which is 0.7 volts below that. Therefore, I know the voltage across this resistor, so I know the current through it. That current must be coming through from the collector here. Therefore, it must be going through this resistor. Therefore, it lowers this voltage by an amount, which is RC times the current, which is the voltage from here to here divided by the resistance, which is 0.7, etc. Okay, and so therefore I can tell you all the bias conditions of this transistor. And now you can use that to check whether or not my assumptions were right, and they are. Okay, now given that incrementally I can tweak this thing, that means this capacitor is now a short circuit. That means I tweak this in voltage, which means this changes by the right amount, which means this current changes by an amount, which is the amount this voltage change divided by that resistance, which means this voltage goes down by an amount, which is the current increment multiplied by that resistance. So the gain of this stage as an amplifier is RC over RE. It's within 5%, that's right. Okay? And every real engineer does that. Okay? And that's not the sort of thing that we were teaching the students. So I wanted to figure out how we could teach students this sort of thing. Okay? And of course, my vision of things is you write a program and then give it to the students to read. Okay? That's what I did. Is I actually hired Richard Stallman in 1975 to work for me, and he and I wrote this program together, and it was quite a success. Okay? And I'll show you a modern version of it because the old code doesn't seem to exist anymore. I went looking for it, and that was on the old ITS operating system, and it's gone. And probably on some backup tape somewhere, which somebody has, it can be found, but it's not around now. So here's a new version of the same program. Here's an example. Here's the representation of that amplifier. I'm not going to tell you I'm not going to read it to you. Okay? What it is, it's a wiring diagram. Guess what? The same lambda calculus combination structure that you use for functions works for other kinds of things too. All it is a consistent naming scheme. It says, for example, let RB1 be a resistor. Let the rail node be a particular node combining a bunch of terminals from the various parts that were declared previously, okay, in the outer scope. And so I have a bunch of nodes. Then I can say I'm going to produce a few more things, and that's the output of that is the rest of the stuff. Okay, wiring diagram, description of how these things are put together. Okay? That's a really nice thing. Remember, underneath this is lambda calculus, nothing more. There's no magic in there. Okay, it's just naming. As a very smart mystic once said, if you have the name of a spirit, you have power over it. Okay? So then, once you do that, then you can, for example, make a test jig for this, which looks sort of like that. Okay, and I can tell it what kinds of parameters I want. Notice, by the way, I'm allowed to use. All my values are also allowed to have units. That's another generic extension. It doesn't matter. It's just simple. Once you have generic operators, you can make units, and it works just great. Okay. I can make various other assumptions about. Here's the transistor assumptions that are pretty simple. I can say what my assumptions are for getting the thing on the chalkboard here. This is to make the arguments short enough to put on one slide. Okay, and then I can ask what's the value of the potential of the base of the amplifier in the bias region, and it does some deduction and it comes out with an answer in volts. Okay, and then you say, well, what's the value of the potential on the emitter, and you get the same kind of thing. Not very interesting, but the really interesting thing is here. I can ask why. Why do you believe, Mr. Computer, why do you believe that the potential on the emitter of the amplifier in the bias region is what it is? And out comes a thing with a remarkable QED that has nothing to do with proving. Okay, it's just to be arrogant. Okay, but what it's telling you is because remember, almost all these things are lies anyway. The models I told you for the transistor are a lie. All of physics and electrical engineering, things like that, is based on useful lies, which are appropriate approximations for particular jobs. Okay? And the reason why, when Galileo invented the modern physics, for all practical purposes, what he discovered was the value of a lie. Aristotle understood that when you rolled the ball along the floor, it always stopped. Galileo said, forget about the friction, let's figure it out, and then put the friction back in. That was a required lie to understand what was really going on. That changed the world. Okay? That was the big breakthrough of Galileo. Okay? So this QED doesn't mean anything, but what really matters is that I'm chasing down the provenance of every value. As the values move around in this thing, and what's really going on here? What's really going on is that I'm doing what the expert did. I'm seeing something very obvious. What I'm seeing is that if I know the value here, then I know the value here because of a local phenomenon. Okay? I'm propagating information around. And if I know the value here, and I know the value here, and I know this value, then I know that value. Okay? And that propagates through here into here, and so on. Okay? So information is propagating around. We call this propagators. And that was a big idea in 1975. Okay? However, it does have some power. Okay? The power is this. Let's go back here. That we have imagined that the propagators are independent little stateful machines that are connected to a number of little things I'll call cells, not biological. Okay? So that a propagator holds a bunch of fingers on a bunch of cells. Given that it knows information from this one and this one and this one, it may be able to deduce the value there and go clobber. Okay? And given that value suddenly got changed, then this guy said, oh, I see something interesting, and it may go change that guy. Okay? So that information moves around, and it's allowed to go in any direction. Okay? But so there are these stateful cells that have state, okay, and there are these propagator machines, and guess what? This is very nice for a very parallel machine. But even better, Alexei Radul, my graduate student 2 years ago, I suppose he got a doctor's degree, made a great breakthrough here. The great breakthrough was that we don't actually put values in these cells. We put information about a value in a cell. And I'll get to that a little later. But what it means is that what a cell contains is a monotonically increasing value of information about a value. It gets better and better information. And as a consequence, things like the synchronization problems go away for a parallel machine. This becomes a very powerful mechanism for building a very large, complex machine in a simple way. But it's an electrical engineer's point of view. It's not a computer scientist's point of view. Okay? It's not data flow. Okay? It's closely related, but it's not. Okay? It's a very different kind of thing because we're worried about information that's being accumulated in these cells. But let me just go a little further. One of the other problems, I hate computer languages now, almost all of them, including the ones I invent. Okay? Okay? And part of the reason is because they're full of expressions. They're even worse, they could be statements. Okay? But they're expressions. And what I mean by that is an expression is a tree. Okay? And you got a bunch of values, and they only go up the tree. And they collected one output. That's what you want to think about it. And you don't have any names for the intermediate parts. There's no name for this place or this place, as in the circuit diagrams you have in an electrical circuit. Okay? And boy, those are useful places to put names on. Now, sometimes they're a pain in the butt. You've got to be careful not to get overwhelmed with names. But indeed, one big difference in this case is I'm going to change it so propagators have all connections are explicit. They have names. So you see, this is a step for the computation of the square root, right? You could by Heron's method, which is sometimes called Newton's method, but it was invented 2,000 years earlier by Heron of Alexandria. Newton did a generalization, which was tremendously important, which is any function, but for square root, it was understood by Heron. What you do is you take the average of the thing you're trying to take the square root of and the guess you have for the square root, and you add that you take the ratio of those, add that to the guess you have, and divide it by 2. So you make the average of the guess into the query plus the guess. Okay? And that converges to the square root quadratically. That's Heron's method. And so that's what this is. And so here's a propagator description, which is a wiring diagram. And indeed, I'm looking now at something that looks very much like, again, assembly language. I haven't got good languages for this yet. Okay? But I'm using lambda glue to put it together. Lambda glue is so excellent for getting going before we understand what the real language is. Okay? So here we have the cells that we're making up, which are all the intermediate ones. This takes 3 cells as inputs, and it says if I want to divide x by g, I put the result in the x over g cell, and add g to x over g and put the result into the g plus x over g cell, and so on. And that's what that is. Okay, so you're seeing a little wiring diagram. For little machines, imagine each of these things is an autonomous machine running continuously. If I can burn processor, I can do that. Right? Supposing I had as much processor as I had memory. Supposing I had for every little memory module, I had a big processor associated with it. Don't worry about that. That'll happen. Right? It's going to happen because there's no other way to make the future happen. Okay? So of course this works, okay, as you expect, and you get a better guess. But now you can also make it iterative. Wiring diagram view of the world. Okay? What are we seeing here? What we're seeing is, of course, a machine, a wiring diagram for a machine. The machine is potentially infinite because it's got a copy of itself right there inside of itself. Right? It's got the Heron step in the machine inside of it, of course. Okay? But this is a way to think about things which is quite different. Okay? Turns out things may have multiple outputs. Okay? None of the ones here do, but things may have multiple outputs. For example, when you divide integers, you get the quotient and the remainder. Okay? That's why have to do one or the other? Okay? Why not even think about that as being the normal way to think? Most processes have that property. Or what if you have things which have many things that go in and many go out? But in any case, okay, we have wiring diagrams like this, and of course, the way in which this guy, square root editor, knows whether or not to expand himself, that's an implementation question, is a question like the difference between applicative order and normal order in calculus, lambda calculus. Are you choosing to expand something when all the inputs are there, or only one input, or you want the output, or anything like that? That's a different question. Okay? I'm not going to worry about that right now. Okay? We can make machines do it any way we like, and we can have policies that can allow you to do both. Remember, a real engineer doesn't want just a religion about how to solve a problem, like object-oriented or functional or imperative or logic programming. This piece of the problem wants to be a functional program. This piece of the program wants to be imperative. This piece wants to be object-oriented, and guess what? This piece wants to be logic-based, and they all want to work together usefully. And that's because of the way that the problem is structured, whatever it is. And I don't want to think that there's any correct answer to any of those questions. It would be awful bad writing a device driver in a functional language. It would be awful bad writing anything like a symbolic manipulator in a thing with complicated syntax. It's awful bad to write a numerical program in anything but Fortran. Okay, that's a joke. Fortran is a wonderful language in some ways. It's the ancestor of them all besides Lisp. Fortran and Lisp are the two oldest languages that still have anybody using them. And I think that they're the keys to everything else, the current version of languages. Okay. But let me go further. Okay, what can you do with these propagators? And I'm only pushing this idea not because I think it's the right answer. I'm trying to twist us so that we say this is a different way to think. Okay, we have to think 52 different ways to fix this problem. I don't know the answer to how to get out of this. I don't know how to make a machine that builds a person out of a cell. Okay. But I think the problem is that we've been stuck for too long thinking about the fact that we've been diddling with our details. We've been sitting here worrying about our type system when we ought to be worrying about how to get flexible machines and flexible programming. So here, for example, yes, okay. One thing I could do with propagators is I can make constraint propagators out of directional ones. If I say that, look, I can make a thing that is an adder that knows that this is the sum of these two, which means if it knows these, it'll compute that. If it knows these, it computes this. If it knows these, it computes this. Okay? It doesn't matter which way the information flows. And in fact, I could do that by just building two subpropagators, which are directional, 3 of them. Okay? Multiplication here is a lie. It's actually a little more complicated because multiplication by 0 has special properties. Okay? Multiplication by 0 doesn't depend upon the other argument. So this is just for show that you're seeing here. And so it fits on the slide. And there are other things like that. Okay, but once I can do that, of course, I can make my electricity stuff. Because indeed, a resistor really is a two-terminal device with a constraint that is I times R equals V, and indeed some other constraints, which is, for example, the voltage is the difference of potentials from the two nodes it's connected to. The currents, some of the currents into those terminals is 0, that the product of the current and the voltage is the power, okay, and that sort of thing. Okay, I can build that sort of machine. So I can build up from what I just showed you. Okay, so that's nice, and it all works very nicely. But the crucial thing here is what I said before, what Mr. Radul invented 2 or 3 years ago for a doctoral thesis. The idea that the cells merge information monotonically. So I'm going to tell you the story about if you've got a barometer, a stopwatch, and a ruler, how to measure the height of a building. There are lots of ways of doing that. Okay? So here's one thing. I can have similar triangles. Okay? That is, I could have measured. I could say the sun is coming in from some direction, except around here at this time of the day, this day. And so there's a shadow cast by the building and a shadow cast by the barometer if I stand it on end. So what I can do is if I'm a ruler, I can measure the barometer and I can measure its shadow. I can measure the shadow of the building if I mark it fast enough so the sun doesn't move in time, and I can measure it out with the ruler, and then I can compute similar triangles and get a value, which is, in this case, if I started out with a building that was, I didn't put units in here, 54, the building shadow was between 54 feet, 0.9 and 55.1 feet long. I'm assuming that that's an interval, which has error. Okay? And the height of the barometer is between 0.3 and 0.32 feet, and the shadow of the barometer is between 0.36 and 0.37 feet. Then the building height is an interval between 44.5414 and 48.978 feet. Okay? That's done by building a similar triangles propagator, which is simple enough. Okay? Of course, I could have done the other thing. I could go to the top of the building, drop the barometer off, and see how long on the stopwatch it takes to go hit the click. Right? That works. Okay? And if I do that, then I can have I use S equal 1/2 AT squared. Whoops. Okay? S equal 1/2 AT squared type propagator. And if I measure the fall time, I can say I can add that to the system. and I get a building height which is 41 point, slightly different, okay? Because of course measurements differ. Okay? They're not the same. But I can do something better. Okay? I can start out with, I can combine these measurements. Okay? That is, supposing I know that the building shadow is this. That's what I measured with my ruler, and I measured the barometer's height and shadow. Then I dropped the barometer off the building and figured out the times. Okay, and so I got a value there. This is a better value if I go down here. If I look, well, guess what? This value. Let me go back here a second. The value here is between 41.163 and 47.243. Here it is 44. So it's a tighter bounds. But the best thing is that information propagates back to the measurements. Hey, the guy who made the measurement made a slight mistake, and we could find it. Okay. Because each of these measurements reinforces the others. Okay? And that's always true in real science. Okay? By the way, how much time have I taken up so far? 45. So I've got 15 more. Good. Okay. Thank you, but I really don't want to talk more than, I'm designed to talk for 50 minutes. Okay? I can talk for 60 minutes on any topic, whether or not I know anything about it. Okay. So each of these values is improved from the values we had before, from the ones we measured. Okay? But now we can, for example, bribe the superintendent by giving him the stopwatch, and we expect to get the honest answer out of this. Okay? And so we get a value which is not an interval, which is 45. He claims the building's height was 45. Okay? Okay, so we get the content of the barometer's height now is better still, and all of these are improved measurements. But I can do better than that. Because in the same way that you invented these hairy monads to be laminar calculus plumbing, which is what they are. They're wonderful stuff, by the way, but they are very hairy for people who haven't understood that very carefully and thought about it for a long time. So in the same way, you want to be able to carry extra information with something. And what a monad allows you to do is to pipe around the value you wish to carry, also state or something like that, that's extra information that gets fed into the right place. So it's hidden plumbing. Okay? It can be done it's a lambda calculus trick that most list-type programmers knew about long ago, but didn't have a name for it. Okay? And it's very useful to realize that it's connected to category theory and things like that. Okay, so what do we do here? Okay, well, tracking of provenance. Okay, well, I'm going to attach other information besides things like units and dimensions and stuff like that. I'm going to carry with it where information came from, so I can make arguments as to where does it come from. You saw that in the electrical circuit case. That's very helpful when you're debugging a complicated problem. Okay, so let's see what that is. All right, well, we're going to start again. Okay, I'm now going to I'm going to make my values be what I call contingent values. Okay? So this value, which I'm putting in the building shadow, is a contingent value which is based on a premise called shadow. It could be several premises, which is why there's a list there. And I'm assuming it's a symbol right now. But the premises they have no interesting structure other than they can tell whether or not two of them are the same. Okay? So these are all shadow premises. And I get answers which are contingent on the shadow. Oops. Okay? I can do the same thing with the fall time. Okay? But this one I'm going to make dependent upon a premise I call time. Okay? The building height now is contingent on both the time and the shadow. Okay? The super gives me an authoritative result. Okay? Then I can look at the building height. Okay, it's dependent upon he gave me that information, but the barometer's height is now dependent upon three things: the superintendent's estimate, the time estimate, and the shadow estimate. But the building shadow estimate is still only on the shadow estimate, and the fall time, however, has been improved by the superintendent's estimate, but not the other one, because the other one wasn't very interesting. It was superseded. The information is monotonically increasing in each of these cells. And the monotonic increase is crucial. Okay? The one way to do that kind of thing, of course, is with things like intervals. But imagine you had unification algorithm, for example. That's a way of combining information. And there are lots of things like that. Right? Suppose I have a Fourier transform of the signal, approximate, and I have a time domain for approximate version of a signal, both with noise. Okay? You can combine those to get better estimates of what that is. So now, this gives us even more power. Because what I'm going to do is assume that, of course, information is usually inconsistent. Almost all the information in my head is inconsistent. I believe lots of things that are false. Right? We all do. Right? But the important thing is that I don't fall apart every time I think, is the famous robot in some science fiction story. Okay? Why? It's because if I run into one of these inconsistencies, I giggle. Okay? That's the answer. It's because I can keep apart locally consistent subsystems of my thinking. And each of those, I can make deductions that I know where they come from, I hope, and they're dependent only on the things that I specify. So let me look at this for example. Again, I'm now going to make these things called TMSs, truth maintenance systems. They were invented, again, originally partly by Stallman and me, but they were given a name by John Doyle, who was one of my graduate students, who wrote a master's thesis about them. His PhD thesis was about something else. And David McAllister did some work on them and made another version of it. And then there's a whole book by two of my former students, Johan de Cleer and Ken Forbes, which is called Building Problem Solvers, which is pretty much about truth maintenance systems. Okay? So there's a whole nice thing. What it is it's a collection of facts, okay, with appropriate dependencies, such that it's possible to say what is the best estimate you can give me of the consequences of these facts, be logical or anything else. Okay? And so in every cell I'm going to put a truth maintenance system instead, which is a thing that's going to maintain the best estimates of what's going on with the ability to back out. Okay? So here's what you're seeing here is that sort of thing. And indeed, I can do all the standard things you saw here. Okay, and I'm not going to go through this, but if you look at what's inside the building height at the end of this little sequence, there's 3 possible contingencies depending upon different dependencies. Okay, and this can grow quite large, but it doesn't grow very large because anything which is subsumed by some other deduction goes away. Okay? And eventually, we can do things like now change our point of view. I can change my worldview. I can bring in, let's see, go back here. Where's a kick? I can decide that I want to kick out the time. Yes. Supposing I want to kick out the time measurement. I want to decide that wasn't so good. Well, I can get a value for the building height which depended only on the shadow measurement. I could bring back the time measurement and kick out the shadow measurement, and I've got something that depends on the time measurement. Okay? If I add the superintendent stuff in and I bring in the shadow measurement, I get something else. I can decide I don't really like the time measurement, and I get the result that depends only on those two. Okay? And I can walk this thing around a lot. Okay? That's a lot of fun. But better than that, I can get contradictions. Maybe somebody made a mistake. Maybe there's a lie. Maybe the superintendent's a liar. Okay? Or maybe the ruler was not held quite right when I measured the height of the whatever. Okay? Look, in real scientific stuff, supposing I have a corpus of all the medical material in the world, all the journals, you know darn well that most of the articles are wrong. Okay? And there's a good reason for that. The reason is that people do experiments with p less than 0.05. Okay, that's that's their measure of whether or not something is good as a good experiment, is whether or not the chance of being wrong is 1 in 20. Okay? Now, since they do far more than 20 experiments, okay, and they only publish the ones that come out positive, okay, you make your deduction from that. There's great papers about this. By Ioannidis, there's a great paper about why almost all medical research is wrong, but we still live better than we did 50 years ago, so it can't be completely true. But in any case, if a physicist walks in with p less than 0.05, he's thrown out of the room. It's got to be p less than 10 to the minus 7th or something for anybody to be interested. Okay. Anyway, so here we go. here what I'm going to look at a contradiction. The contradiction depended upon the superintendent of the pressure measurement. I was measuring this one. I used the barometer a second time. Maybe I had two barometers. Okay, so I'm getting back here. And I measured that by a pressure measurement, which I suppose I didn't put on the screen, which of course you know the difference in pressure from the height as you move the vibrator up and down the building is going to be the weight of air between those two. Okay, and so I got a contradiction between those two, and I can decide which of those I like or don't like, as you can see here, okay, or here. Okay, I get two different values. So I can maintain a inconsistent worldview, a major inconsistent worldview, by having locally consistent worldviews. But better, okay? Yes. Even better, I can also have the machine automatically find for me the consistent sub-worldviews that are consistent. What worldview is consistent? That's called dependency-directed backtracking. And unlike chronological backtracking, which you would get, say, by using the sequence monad and a failure mode, right? For those of you who are Pascalites, okay, that would give you a chronological backtrack. Unlike that, I can do much, much more efficient backtracking because I know the provenance of every fact. So I can say, if I got a contradiction here, okay, and I've got another contradiction, and the intersection is this guy, it's highly probable he's the bad guy. But even so, if I just find something to rule out, okay, I can rule out a whole subtree without having to undo anything and redo computations that were already correct, okay, but they were chronologically later. Okay? Remember this because it's a parallel machine. In principle, it's right now simulated serially, of course, by a little time-sharing system. But parallel machine with where all of these things are independently looking at information and carrying them from one place to the next. Okay? So here's an example of the famous story. There's a 5-story building. Baker, Cooper, Fletcher, Miller, and Smith live on one of the 5 floors. Okay? I require that Baker, Cooper, Fletcher, Miller, and Smith live on distinct floors. That Baker is not on the 5th floor, Cooper is not on the 1st, Fletcher is not on the 5th, Fletcher is not on the 1st, Miller's on a higher floor than Cooper, and the Smith and Fletcher and Cooper are not on adjacent floors. Okay? And I want to know what the answer is, and it's pretty easy to get. It's very, very efficient. If I did this by a chronological process, this would be 3,000 or something backtracks, okay, to investigate this space. Not that search is a good thing. Search is always exponential and will always eat you if you let it. So this is not to say that we should be doing search. It's just showing that I can automatically find consistent subsystems of a complex system because this is working by backtracking on inconsistencies. Okay? Now, let me go back to the original thing I was talking about at the beginning. Okay? When I was an undergraduate at MIT, I used to walk by Jerry Letvin's lab. Everybody know who Jerry Letvin was? Who does? Okay? Everybody hear of the Letvin-Leary debates? Or debate? Or anything like that? He was a famous neurophysiologist who was the first person to measure potentials from neurons. And he did it. He made great amplifiers. He was professor of electrical engineering and biology and humanities at MIT. Okay? And I used to go by his lab, which said Laboratory of Experimental Epistemology. On the okay? Yes, I was employed as one of Minsky's computer hackers. Okay, so I would go over there and I'd pass by the Letvin's lab, and I'd drop in and listen to him talk about wonderful things about neurophysiology and things like that. And one thing that Letvin, he died, by the way, last year. One thing that he would explain quite often, is that almost all the cells in the central nervous system are very tiny, much tinier than the ones that you hear of that have long axons and things like that. And it's really hard to see them even with a good microscope, and it's pretty hard to measure potentials from them, action potentials and things like that. So he had this idea that they actually are, besides being undercounted, that they may be, a hypothesis, many of these neurons are not explicitly directional, that they are actually things that are like these constraints, that feel a bunch of other things and adjust the sensitivity of other neurons they touch. Okay? So if they say, gee, I feel these three things be doing something, then they say, oh, maybe make this guy do something too. Okay? But if it's only these two, then I better make this guy do something and leave this one alone or inhibit this one. Okay? That was a kind of idea he had, which might be false. I'm not trying to suggest it's true or false. I don't know. I don't know anything about neurophysiology. Okay? But except for what I've learned by walking into Levin's lab. But the... Oh, yes. He could talk about any... Oh, I could talk about it for an hour, too. Sure. Okay. But getting back to the kinesis triangle illusion, is it possible that almost all the computation that we see that's really fast is filling in details? What is going on in that electrical circuit example I showed you? Even with a big circuit, it's filling in details that the diagram is a memory. And I'm writing in specific, well-known, defined places the answers that I can deduce from local information. Okay? Sometimes I have to invent a variable and propagate it around and get an equation, but I hope not very often. Okay? But most of the time by picking my models correctly, I'm choosing to make the problem simple enough so I can do this kind of propagation, which fills in details. What's happening here? What's happening here is this guy is giving me evidence that there's something including this black circle. By golly, there's good evidence here that this black triangle is being included by something too. Okay? Maybe there's good evidence, that's good enough evidence to think that maybe there's a white thing that connects these. Okay? And things like that. Okay? And maybe that's done by some magic process that looks something like that for all we know. Okay? I don't know this is true. I don't claim it's true. Okay? It's a different way to think. Maybe it's worth investigating. It might be completely nonsense. On the other hand, we have to throw away our current ways of thinking if we ever expect to solve these problems. So, in summary, okay, I'm claiming the problem facing us as computer engineers is not correctness, it's evolvability. A trivial example of making things more evolvable is that extensible generic operations may help. Okay? Because they allow us to extend functions without modification, but they make proofs very difficult. A more radical proposal is maybe there are freedoms that we can unlock by throwing away our idea of architecture. Okay? How machines have to work. Here's one particular example, which is concurrent and parallel in an essential way. It's redundant and degenerate, meaning it's possible to compute the same thing many times and put them into the same place, and it doesn't cause any trouble. Except if one of the things dies, you get the correct answer another way. It can be degenerate, means I can compute it a different way. The same way I can compute in my physics class by Newton's vectoral methods. I can compute the motion of something like the planets. Okay? I can compute it by the Lagrangian method. I can compute it by the Hamiltonian method. They get the same answer, but they reveal different phenomena. I'm not going to find out about how the symmetries in the system correspond to the conserved quantities if I look at Newton's method. Okay? That's why I want to see Lagrange's. If I want to do a canonical transformation, it better be Hamiltonian. Okay? So there are all these. That's what degeneracy means. Many ways of doing something. If I can't eat sugar because I'm screwed up in some way, okay, then I can get my calories out of proteins. Okay? Every biological system has many ways of doing things. That's called degeneracy. Okay? I can maintain provenance. That is, I can know where data comes from and follow it around. And when the data combines, I can combine the provenances appropriately. Sometimes you have to subtract, as in a conditional proof. If you say, assume A, conclude B, therefore you can conclude A implies B without the assumption of A. So there are certain kinds of rules that have to delete provenance when they do it. But you have to know that. So the means of combining provenance that have to be taken care of. Okay? And I can tell you about dependency-directed backtracking, which is a useful way of controlling non-deterministic search sometimes. Okay? That's an example of things that I'm just pushing forward as being a possible way to break out. But I want to hear every way that can, and that's all I have to say today. Okay?